Okay, recording is restarted. So now you guys have some time to think about this, work with each other. I'll take you guys through my example wheel with my numbers. And yeah, you guys can use this model and check your work and see how you did. So first guiding question here was, how far does the light actually move going to the mirror and back? Well, I have a 3 kilometer distance. So I'm going to double that, make it 6 kilometers, but also see where it says meters. That's always a good idea, is to convert to base SI units. So guys, 6 kilometers, how many meters is that? 6,000. Okay. So if you had a 3 kilometer gap, 3 plus 3 is 6 kilometers times 1,000 to convert to meters, 6,000 meters. Okay. Next question, how much time would it take the light to travel back and forth? Okay. Again, we're working backward from the answer because you guys know what speed of light is. So, hey, if you have a distance and you have a speed of light, isn't distance equal to speed times time? So if you're solving for time, shouldn't time just be distance divided by speed? Right? Okay. So the distance is 6,000 meters. And the speed is, open parenthesis, 3 times 10 to the 8 meters per second. I'm getting 0.00002 seconds. If you like, you could also call that 2 times 10 to the negative 5 seconds, if you like scientific notation. So pick your favorite version of that. Okay. Of course, everybody's numbers are a little different, but you should get something on that order of magnitude, right? A tiny, tiny, tiny fraction of a second for this whole process to happen. Right. Next question, how far should the wheel turn in during this process? Right now, I think that this box right here is probably the hardest part of this whole puzzle. Okay. So, right, how far does the wheel have to turn? Well, it depends how many teeth are on your wheel. Let me give you guys a simplified example here. What if okay, so this one's going to be kind of ridiculous, but sometimes if you come up with ridiculously simplified examples that shine some kind of light on how you have to do this. What if I have a 2-tooth wheel? So this wheel now has 2 teeth. You guys see that? Okay. So for the light to go through this gap and then come back, and then this tooth is now in the way, how much of a turn is that compared to 1 revolution? It's what fraction of a revolution? A quarter. Yeah. So if I have 2 teeth, doesn't it have to turn a quarter of a revolution? Huh. What about this? You guys might see a pattern already, but maybe I should give you guys 2 examples so you can for sure make a pattern. What if I have a 3-tooth wheel? How far would the wheel have to turn? 1/6 of a revolution? Huh. So if you count the number of teeth and the number of windows, isn't that like 2 teeth, 2 windows is like 4 things? Okay. And then you take 1 revolution and divide by that, right? You guys got that? So you can make your own formula that will answer this box. Maybe that's why this one's hard, is because you have to come up with your own expression. But instead of 1 revolution, I'm going to do radians. So 2 pi radians would be 1 revolution, right? So take 2 pi radians, which represents 1 complete turn, and divide by 2 times the number of teeth, because it's number of teeth plus number of windows, right? Right? You guys have that? So now for me, I have 29 teeth. So what is 2 pi radians divided by, open parenthesis, 2 times 29? I'm getting 0.1083 radians. Okay. You should get something kind of like that, like a fraction of a radian. Okay. Now pause right here, because here's one of the things I want you to get out of this class too, is think, well, if I change something like the number of teeth of this experiment, how would that affect this? And would it, for example, guys, what would be easier to work with? A wheel with 2 teeth, a wheel with 29 teeth, or a wheel with 1,000 teeth? Let's say you're the experimenter back in the day. Which one of those wheels is probably easier to do this experiment with? I'm thinking 1,000 too. Yeah, I like that. Because 1,000 teeth, wouldn't that have to barely turn at all? Right? And so maybe the wheel wouldn't have to spin as fast. right? So maybe it's just a thought, right? But that's the kind of connections that I want you to see in this class. But yeah, you guys got that, so awesome. Right. You know what? If you got that far, you can actually solve this whole thing in one step. Because the question is, how fast does the wheel have to spin, which is called angular velocity. We've been referencing that with Greek letter omega. Isn't that just how far it turns divided by how much time? Here's how far it turns in radians. Here's much time in seconds. Hey, could you do this many radians divided by this many seconds to get this many radians per second? That will answer the whole thing. So no, I'll take you guys through the rest of this too and show you this different point of view. But if I take this many radians divided by this many seconds, I'm getting this number for my paper. Now, my paper is different from everybody else's, but you should get so many thousands of radians, right?
Like, I got a big answer. I just thought that's unrealistic. I thought,
Yeah.
how do you spin a wheel that fast?
Yeah, that is a good question too. Yeah, how would you do that? I don't know. Whether you do like maybe hooked up to steam power or something. I mean, I guess they could do that. But
No.
yeah. All right. Now, there is another way you could solve it. Oh, did you guys see, by the way, that we never touched the sides of the wheel, like the diameter of the wheel? We've never actually used. Huh. So that ends up canceling out. Interesting. But what if you went on somewhere else to solve this problem that did utilize that value? And that's what these last two boxes are. So we'll solve this a different way and see if we get the same answer. I hope we do. What is the radius of the wheel? Well, I gave you the diameter in centimeters. So guys, to go from diameter to radius, what do you do? Divide by 2. So I have 108 centimeters, divide by 2. So that's 54 centimeters. And to go from 54 centimeters to meters, you divide by 100. So my radius is 0.54 meters. Right, so diameter divided by 2, and of course divide by 100 to convert to meters. Question after that: how far would a tooth or a window, for that matter, move during that process? Remember, it just like turns a few degrees, kind of thing, right? Or well, this many radians. So here's one way you could do this. You could say distance that a tooth moves is equal to how far the wheel turns, angular displacement, in radians, multiplied by radial size of the wheel. You guys remember that? That's why I was referring to that poster on the wall with the circle on it. You guys remember how to convert back and forth between angular and linear motion? So how far does the tooth move? Well, I know that my wheel turned 0.1083 radians, multiplied by a 0.54 meter radius. I'm getting 0.05848 meters. Isn't that about 5.8 centimeters? If you like that, that's about this distance right here. Right? You can model that. That's the distance that a tooth on my 29 tooth wheel with this radial size would have moved. And last box, what's the linear speed of a tooth, or a window for that matter? Linear speed. Hey, isn't that how far it would have moved divided by how much time? And how far it moved? Well, that's this box right here. And how much time? Well, that's this box right here. So let's do how far it moves divided by 0.05848 divided by 0.00002. I'm looking at 2924 meters per second. Okay, so it's like radar gun speed, like speedometer reading on your car, so what do we do? Okay. Now, if we already got the answer to this main question a few boxes ago, why are we doing these 3 boxes? Well, because this is a different approach, right? A lot of times, you guys see over and over in this class, a lot of times there's like multiple ways to solve problems, and this is an example of that. So how could you play off this set of numbers to also confirm this answer? Well, how fast something spins, that's called angular velocity, Greek letter omega, isn't that linear velocity divided by radial size, right? And linear velocity is that number there, and radial size is that number right there. So I can take my 2924 meters per second linear velocity, divide by 0.54 meter radius, and I get 5,415 radians per second.